Sorry, I'm so sorry. Welcome to everybody. Again, it's a pleasure to me to introduce you Professor Joao Gomiji. Today he will talk us about supersymmetric gauge theories and also Joao's institutional affiliations are IFT UNESP and ICTP Cypher, and now he is currently visiting Harvard University. So um, Joao, thanks a lot to be here, and the screen is yours, so we can start.
Okay. So, can you guys hear me? Is everything okay? Okay. Okay, great. So, thanks a lot, everyone, for um for inviting me. It's really nice to be here. I know that there are some of my friends from IFT who also spoke at previous days. That Dennis, who's um my friend and my colleague, has the same supervisor as I do. Uh, he's, he's been giving a course in supersymmetric field in supersymmetry. So the idea will be to talk about some stuff related to what he taught in the course, and to and for that I'll be discussing this subject, which is d equals 4 and equals 2 supersymmetric gauge theories, which is which was the subject for my master's dissertation. So right now I'm working on a different topic, uh, which is string theory in my PhD, but um, nonetheless, I think that this is a very beautiful and and important subject. So hope that you guys like it. So okay. Um, so to start, I'll just make some initial remarks, and then I'll try to explain what is d equals 4 and equals 2 Spring Mills. And then, as I said in the abstract, I will cover two kind of applications of d equals 4 and equals 2 Spring Mills. Um, the first one, which is Seiberg-Witten theory, is the thing I'll spend most time on, which was a big deal in the 90s because, well, you'll see later, it's a pretty powerful tool to study supersymmetric theories. And the last subject is twisted Spring Mills, but in this case, more precisely, I want to talk about how this twisted Spring Mills theory is a topological quantum field theory, and it has some nice connections with mathematics and so on. Okay, so to start, maybe Dennis already said that, but supersymmetric theories, they usually allow you to investigate them in a deeper way because they have a lot of structure. So because you have these extra generators in the global symmetry algebra, you have these protected quantities, all of these things, and things have to fit in nice multiplets and everything. You have a very rich structure, which usually allows you to make conclusions that are not as available in non-supersymmetric theories. And I'll try to convince you with the examples I'll discuss here why that is the case. As I said, they also have many connections with other areas. So most notably for the this thing that I did in my master's, where it was the connection with mathematics, just pure mathematics, which is really beautiful, I think. And also for the stuff that I do now, which interests me the most, is it also has a lot of connections to string theory. So superstring theory is already like a supersymmetric theory. It has supersymmetry and um, well, that's just one example how it ties to string theory. So as I said, Seiberg-Witten theory is a powerful tool to study supersymmetric field theories because it was one of the first instances where um, you could actually compute exactly how the theory behaves at low energies, and it also provided a framework to study or to understand confinement in a quantum field theory. Of course, like everybody wants to um, understand confinement in QCD, for example, but QCD is not supersymmetric as far as we know. Well, the standard model is not supersymmetric. I have to go beyond the standard model. Um, and but here, because the theory is supersymmetric, we can touch or study or understand confinement in a better way. So I won't discuss confinement here in the talk. I'll just say how you can like find this low energy effective action, but this is already a super non-trivial uh, non-trivial thing that you can do and that they Cyber and Whitman were able to do. Um, and the second point, as I said, is topological quantum field theories. They usually like have some notion of supersymmetry in them. And this thing that I'll discuss today is maybe the first instance or one of the first instances where topological quantum field theories appeared. Okay, so I'll start by discussing what is d equals 4 and equals to Spring Mills. So d equals 4 means we're in 4 dimensions. N equals 2 means that we have two sets of supersymmetry generators, or we have two supersymmetry generators. And Yang-Mills means that we want to discuss a theory, a gauge theory. So, like QCDs, well, at least I call it a Yang-Mills theory. So it's a theory for gauge bosons, and maybe you can add some matter. Here we'll see that you have the gauge bosons as usual, and some other particles that make up this supersymmetric multiplet, and which are the super partners of this gauge boson. Um, okay, so as I said, we start with two supercharges or two um, sets of supersymmetric generators, and there will be 8 in total because of the spinor index, which in 4 dimensions ranges from 1 to 2, because they're chiral, anti-chiral, vial or anti-vial, and this uppercase letter A labels which set of supersymmetry generators you're talking about. So this is maybe, I don't know if Dennis covered this during his course, but this is like, if he only covered n equals 1 supersymmetry, then this is like you have two copies of the supersymmetry generators. And the algebra is the thing that you probably saw in the lectures, so it's just this thing here. So P is the translation generator, and we see that Q squared squares to P with this Pauli matrix. And here the delta AB just says that you have this commutation relation if the A and the B are in the same um, set of supersymmetries. And the nice thing about that, so the rest of the algebra also follows, so the Lorentz or the rotation generators rotate the spinors like with the Pauli matrices and so on and so forth. But the cool thing is that now you can have a central extension in the algebra, which is the second commutator that I have written here. Um, and this central algebra or this central extension is given by this generator ZAB here, and it is supposed to be a generator which commutes with the rest of all of the generators in like the supersymmetry algebra. And so this will be important to us because it will like later we'll see that the existence of this central extension is important for the field content, or not the field content, but the allowed states in the theory. Okay, So far it's like basically the same thing. Apart from this, it's pretty much the same thing that you guys saw in Dennis's course. And now I'll discuss a little bit about the representations. And for what I'm speaking, I'll be talking about just the massless representations. Of course, you can do massive representations as well, but here we'll focus on the massless ones because we want to find the multiplet associated with the gauge boson for this Yang-Mills theory. Um, okay, so for a massless field or massless particle, um, you can like go to a frame where the momentum is like this. And from the supersymmetry algebra, you realize that the commutator for the supercharges is given by uh, this matrix, where the indices are the spinorial indices. And this is just, you just find this by acting with P on the on the massless states, for example. Um, and from that, we see that this commutation relation, it is only non-zero for the first entry. So for example, alpha and alpha dot being equal to 1. And for those specific components, or for those specific indices or supersymmetry generators, this is precisely the algebra for creation and annihilation operators. Um, so if you like just renormalize Q and Q bar, you can define these creation and annihilation operators such that they satisfy the usual commutation relations that you expect. Um, and then, now that we have this, we can start creating the different states in the theory by acting with the creation operator on some vacuum with helicity or spin h. So since these operators are fermionic, because Q is fermionic, we have um, one state without the action of any operator, which is just this omega here of helicity h, which I've written down here. We have two uh, states with helicity h plus 1/2, because the helicity of Q is 1/2. And we have two of these because we can either use Q1 with A equal to 1 or Q1 with A equal to 2, a Q bar, that is. So we have these two states. And finally, we can only act with an extra supersymmetry. So if we acted with Q1 1 dot, we can only act with Q2 1 dot, Q bar that is, and we get a state with helicity plus 1. So in all, we have, for starting with a ground state with helicity 0 or spin 0, we can construct this vector multiplet. So we have a scalar phi, which is this thing here. We have two spinors, which I'll call psi, which are these guys. And we have our gauge boson with spin 1, which is this guy here. Um, and we have the complex conjugates of all these states. So this is like the field content, if you wish, of supersymmetric Yang-Mills, pure supersymmetric Yang-Mills. Of course, this is not the only type of spectrum you can have on a supersymmetric or equals to supersymmetric theory. You can start with um, ground states with, or omegas with different helicity, and for that case, we'll get a different spectrum here, or a different multiplet. And for example, you can have a multiplet with spinors and scalars and so on. But since this will be important if you want to like add matter to the theory, because if you have a hypermultiplet with scalars and spinors, this is kind of the matter of your theory. But here I'll discuss only pure supersymmetric Yang males, and these are the guys who show up. Okay, so this is basically um, the thing here is that A is simply the thing you usually have in Yang males. If you had n equals 1 supersymmetry, you would get also its super partner, which is psi, which will be like the gaugino or gluino or whatever you want to call it. And but here, since you have two supersymmetries, there are more superpartners. So you have two gauginos and this scalar as well. Okay, so this is just more explicitly the set of states we have, how they transform under the different um, charges, global symmetries of the theory. And in particular, I want to stress that we have this internal symmetry here, which is called R symmetry. And this SU2 times U1, it rotates the two supersymmetries in the theory. So it exchanges one for the other, and in particular, it under this R symmetry here, these guys, the psi's are double, so they turn into each other. Okay, so now we go to the question of how to write an action for this theory, which respects n equals to supersymmetry. Um, we can either like take what we know for usual n equals one supersymmetry and try to guess or like adjust the theory so that things conspire and work, or we can make n equals to supersymmetry uh, manifest from the get-go. So in the first route, we just like take the usual stuff that we know about constructing um, supersymmetric actions, and as I said, you just tune the coefficients or the allowed terms um, to 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 make n equals to supersymmetry be a thing. Um, Here, the key to this is that you can actually like um, separate these these things into two n equals 1 multiplets. So you can have a scalar multiplet if you take one of the psi's and one of the phi's, which probably you've seen in class. And you can also have a vector multiplet if you take the a and one of the psi's separately. So this is the thing. This is kind of the idea of how you can get an action from n equals 1. You separate these two multiplets, tune coefficients so that the transformations work, and you'll end up with an action like this. So the W here is like some field strength for, not some field strength, but it's like a potential for the vector multiplet, and the A's are the scalar multiplet. This is the interaction between them. And yeah, so this is one thing you can write down knowing supersymmetry and tuning the indices. The second route is that as well as, so you can try to like build a n equals 2 superfield. So maybe you've seen in class that a n equals 1 superfield is the natural thing to consider in superspace if you want to build n equals 1 supersymmetric quantities. So the idea will be to generalize this notion to n equals 2 by introducing more coordinates in superspace and writing the action also by um, writing an action which depends on this superfield and which you perform this Berezin integration or fermionic integration over the superspace directions or coordinates. So you don't have to worry a lot about the expressions, just the general idea that you can generalize superspace prescription or the superspace intuition to like n equals 2. This is not always the case. For higher supersymmetries, it's not always possible, but for n equals 2, you can define this n equals 2 superspace and write an action this way. So here it is like an action where you integrate over the usual four-dimensional um, space-time directions, but you also integrate over these super coordinates, theta and theta tilde. So for example, n equals 1, you just get d squared theta. Okay, so the, the, the important thing here is that anything you write with psi, where psi is the superfield, which depends only on this, uh, which has no bar on it, so it has no a bar or w bar and so on. Everything you write with psi will be n equals to supersymmetric. So in principle, this is not the only expression you can get for an action. For the classical action, if you expand the components and you want a renormalizable theory and everything, you want stuff to have the um, right terms, like this f squared term, the interactions with the fermions and the scalar being like this, and so on, then that phi squared is the thing you write. But if you want to do a quantum theory, um, there can be quantum corrections, and the action may get different looking terms. Um, so here, just to say a little bit about the section. So this is just the thing you get in pure Yang-Mills as usual. So it's just f squared. This guy is like will be important later because it kind of counts the number of instantons in your configuration for the gauge field. Um, this is the second line is the usual coupling of like any spinor or any scalar in a theory which has gauge fields. So this is the covariant derivative, right? So it's d plus like the commutator of A with the fields. And the last terms, they are here because they're kind of self-interactions between the fields, and they're here to make like supersymmetry transformations work. So this isn't, I mean, this is kind of like the natural generalization. If you've seen like n equals 1 super Yang-Mills, this is I guess this is not so hard to like believe that this is sensible action. Okay, so this is the classical story. I want to discuss what are these quantum corrections. Um, so as I said, this is just basically the thing that I said before. The quantum corrections may add a function of psi to the theory. Um, and in general, the expression will, for general f, the expression will look like this. Fab is the derivative of this function with respect to the scalar multiplet. This is basically just like it's basically a more general form of this thing here. Um, and so our task will be determining what is this f function here. So we have the first term, which is just psi square, but we want to see what are the other terms in the quantum regime. To do so, we will use this thing called Seiberg-Witten theory. Um, and the key about Seiberg-Witten theory is that because you have so much knowledge about the theory due to the fact that it is supersymmetric, you can like take conclusions and build extra structures or auxiliary structures that allow you to fix what this function f is. And the key here will be to investigate what is the space of vacua of the theory. Um, when I say that we want to determine the quantum corrections, and when I say that we want to determine the low energy effective action, I mean the effective action in this Wilsonian sense. So this is like if you have a path integral to compute like stuff as you usually do in quantum field theory. If you have a path integral, uh, you have integration over the fields and you have the exponential of the action. Um, so the idea behind Wilsonian effective action is that you want to look at the theory at a specific energy scale. And in this case, we want to look at the theory at the low energy scale. So the thing you do is you integrate out the high energy modes of your fields. So you integrate everything which is very massive, which is has large momenta and everything. And this basically is what's written inside these parentheses here. And when you perform this formal, like, or in principle, integration, you will rewrite your path integral as like an integral over only the low energy modes of the theory with some modified action, which is this effective action, which I'm calling SF here. Uh, and the thing is that because you're integrating um, all of these high energy modes, you can have all sorts of different interactions appearing in this effective action, and it is usually pretty tricky to determine what it looks like. And we'll see that there's a miracle happening in cybergroup theory that we can actually compute it. So basically what I'm trying to say is that um, we want to determine what is this prepotential, is basically which will basically tell us what this effective action is. And the only thing we have so far is that it depends only on psi, not psi bar. Okay, so we'll start by, as I said, looking at the moduli space of vacua. And so the whole story that I said here, it it works for any gauge group in principle, and so you can have SUN or SO whatever. You can have different gauge groups, but I'll just focus on SU2 because it is simple. The expressions are tiny, and it captures all the essential um, all the essential aspects of what I'm trying to discuss. And also, uh, well, the paper was originally they just talked about SU2, so that's also a reason why. So the first step is characterizing what this moduli space is, of vacua is. So in a we want the vacua to be like for the scalar for a thing for which the scalar potential vanishes. So this commutator being zero, and because all the phi's they have these indices in the gauge group or the adjoint representation. These phi's they're matrices from the point of view of the gauge group, and we can have non-zero phi's such that the scalar potential vanishes. Um, and this is achieved if you take um, the phi's to be in this thing called Cartan subalgebra of the Lie group algebra. So this algebra is the maximal number of generators which commute amongst themselves. So if phi is a matrix which commutes with itself, then for that particular component or for that particular generator, uh, this commutator vanishes and you have a vacuum. You have a potential with which is like evaluated to 0, and this preserves supersymmetry. But since you're taking like a fixed direction for the vacuum, the gauge symmetry is spontaneously broken. So it is spontaneously broken just to this subgroup of or for this particular generator that makes the commutator disappear. And here I've written down what this particular generator is, or what this particular vacuum configuration is. It is just given by this 2 by 2 matrix here, where A is some number. And there are a few inequivalent choices, non-equivalent choices for this. You can have like rotations, or you can like change A to minus A and so on. There's some ambiguity in defining this guy, and this is because of this vial group of SU2, which kind of rotates the generators among themselves. So the true coordinate for the moduli space will be this u squared, which is invariant under the action of this vial group. Okay, and so for SU2, at the end of the day, you take this to be your vacuum configuration. Your gauge symmetry is broken from SU2 to U1. You are left with a U1 gauge theory, so you have some sort of electromagnetism still. And the coordinates for the vacua will be this U. The A will still be important, but it will be some auxiliary thing, or some auxiliary description. Okay, so this is like the first type of characterization of the moduli space of vacua that we have. So it is basically the different values of u. Okay. Um, so before we proceed, I just want to talk a little bit more about what is the thing we want to do with this prepotential. Um, so of course, usually you can do like perturbative calculations in quantum field theory, and you can like go very far with it. Because the theory is supersymmetric, usually it happens that perturbative corrections just truncate at some point, and this is the case here. We only have a one loop perturbative um, contribution to the prepotential, which is this first term, um, and it can be extracted from the U1 anomaly of the U1 symmetry we have discussed in the beginning. So I guess that on Miser will talk about anomalies today later, so you'll get better um, a better taste of what these anomalies are next in the next talk. Um, but you can also have non-perturbative pieces which are not accessible through just doing perturbation theory or taking, or in other words, the regime where the theory is weakly coupled. And this is usually really hard to compute. And these are precisely the guys which we want to like determine today. So we basically, so that this, for this theory in particular, the non-perturbative piece has this phase here, and we basically want to like, well, we want to write, we want to find what this whole thing is, but in particular, the difficult thing that we want to do is determine how we can get these f's for the non-perturbative piece. Okay, so now going back to the moduli space, um, that first like characterization was not a complete story, um, mainly because a, or the coordinate a or u that we had before, it is not a global description of the moduli space. So if you look closely at the at how the action is written, you can like associate the coupling of the theory to the expression for f for this prepotential. Even though you don't know it yet, you can characterize the coupling for the theory in terms of the prepotential, in terms of how it is a function of this of these variables a, and in terms of the variables u. And you conclude that if a was a global coordinate, then there would be regions in this space where um, this gauge coupling would be negative. And since we have like as we saw, since we have the coupling here in the potential, the scalar potential, if we have a negative coupling, then the theory is just unstable. So you can have states with uh, like arbitrary low energy. So this is not the case. We want things to make sense. So A, it can only describe um, the moduli space locally. So this is basically, I think that you also guys, you have also discussed like general relativity and um, like differential geometry. So this basically saying that the modular space is a manifold, um, and you don't have a global description, but you have to look at patch by patch. Um, okay, so this is the first extra information we have about the moduli space. The second information that we have is that there's a dual description. So you can define this dual coordinate in terms of the prepotential, in terms of the derivative of the prepotential in terms of A. And this is also related to the coupling of the theory. But in this dual description, you can like, what I want to say about this dual description is that you can rewrite the the theory in terms of this dual coordinates A, D. So it's like you have um, a dual um, scalar multiplet. And if you rewrite the theory in terms of this dual fields, you see that you're exchanging strong and weak coupling. So the gauge coupling, the effective gauge coupling of the dual theory is the inverse of the gauge coupling of the original, or yeah, the original description. And so you have an exchange of strong and weak regimes. So this is another important thing um, that we have in the description. And finally, we have the theta angle in the action. I don't know if you recall, is the term with the instanton counting term there. And the theory is independent of, it is symmetric under you adding +1 to this, to the theta angle, adding 2 pi to the theta angle. So you have this set of duality generators which act on the coordinates of your theory, and you you have this all these different descriptions. So these generators, they make up this SL2. So the group is bigger, but I'll just stick to SL2 to Z. Um, so we see that if we want to like characterize this moduli space, we have to take into account this duality, this moduli space, or this, not the moduli space per se, but the the auxiliary space of A and the dual A. It has this nice property that it is, it transforms well under this SL to Z duality. So yeah, basically this is the summary. So we have the moduli space of Aqua parameterized by U. U is not a global coordinate. We can build this auxiliary space X, call it X, which is parameterized by the dual coordinate and A. We see that it has the nice property that this duality group acts on it in a nice way and gives you like different descriptions of the theory. And so far it's pretty much artificial, I think. So that's at least that was the first impression that I had when I was first studying this subject. But it's actually this auxiliary space that holds the key to the solution of the problem. So before we go to the solution per se, um, we see that I want to discuss a little bit more about um, the content of the theory, which is the last ingredient to tackle the solution. So, as I said in the beginning, since we have extra supersymmetry, we can have a central extension, which is the Z generator that I talked about before. And this Z generator, it allows you to have a set of states or a set of states in the theory, which is very special because it is a massive, these are massive states, but they live in a short multiplet. So as I said in the beginning, when we were talking about the representations of superunion mills, I didn't discuss the massive representations, but we can just repeat the analysis that I did before. And if you repeat the analysis that I did before, uh, and you like write the creation and annihilation operators, for a massive state, we see that we have more more guys in the multiple. So this is the general story. And however, if you have more supersymmetry and you have this central extension in your algebra, you can show that there are special states which preserve some supersymmetry or are annihilated by some supersymmetry, which actually live in a short multiplet which has the same number of states as it's a massless multiplet. And these are the so-called BPS states. And the important thing for us is that they exist also in Seiberg-Witten theory, in n equals 2 d equals 4 spring mills, on this vacuum, because the vacuum, giving a expectation value for the vacuum, or that VAV that I wrote before, it actually introduces this central extension to the algebra, and the states acquire, there are states which have a mass, and this mass will depend on these coordinates that I talked about before, which are the values of this VAV A and AD. And since we have a notion of, like, we still have this U1 gauge group surviving, and I said that we have this notion of electromagnetism, it will also, the mass of these VPS states will also depend on how they are charged under this remaining um, electromagnetism theory that we have. Okay, so the thing here is that um, these guys are massive, but it is very clear from this expression that there may be certain values of um, magnetic and electric charge and A and AD for which this mass vanishes. So at these points, the moduli so you have to recall that A and AD are functions of the U coordinate on the moduli space. So at the weird thing here is that at these points in the moduli space, these states which were massive, they're actually massless. And as I said before, we're doing Wilsonian effective theory. We're integrating out high energy modes, and in particular here, we're integrating out massive modes. So at these particular points in the moduli space of Aqua, where we have these massive states becoming massless, this procedure that we had before of just integrating out the massive um, degrees of freedom, it's just wrong because we were integrating out stuff that we are not allowed to integrate out anymore. And this will introduce these things, these monodromies or singularities or whatever in our description. Um, okay, so basic idea I want to give you is that we have some massive states in the theory because we have a central extension. These massive states live in a short multiplet, and for specific points in the moduli space of vacua, the masses of these guys vanish. At these places, our procedure of integrating out massive modes to have like Wilsonian effective action is faulty, and we'll get some information from that. So, okay, so now I'll start giving you the solution to the problem. It's fairly technical. I'll try to go fast through it just to give you a taste of what's happening because I want to get to the topological quantum theories also. But okay, so the deal is now to see what are these monodromies in the moduli space of vacua. The first one is already present at the level of the one loop correction to the prepotential. So we see how our coordinates in the auxiliary space transform along a loop of like taking u to e to the 2 pi iu. We see that one of our dual coordinates goes to minus itself. One of our coordinates goes to minus itself. The dual coordinates go to minus dual coordinate plus 2a. So we have this M infinity matrix acting on our coordinates. So this is a further characterization of the auxiliary space that we constructed. So you can think of it this way. Okay, for the monodromies at low energy, these are the guys that I just told you about. These occur at places where we're integrating out these massive particles which become massless. Um, we will take some point in the moduli space where the dual coordinate 0 um, and perform the same thing. We write the dual coordinate and the original coordinate in terms of u at this point and see how it changes as u goes to 2 pi iu to characterize how these how the, the auxiliary space looks near this point. We'll see that the coordinates at these points get transformed like this. So this is their transformation, and this is the matrix which checks on the transformation. So here the matrix is supposed to be like acting on AD and A, this vector. Okay, and finally there's also a monodromy at minus U because of Z2 symmetry in the U plane. So everything that happens at U happens at minus U. And you can just find this matrix as well, and it is given by this. So the first monodromy comes from monopoles which become massless at this specific point, and the second monodromy comes from dions, which are particles which have electric and magnetic charge, which become massless at this point, minus 2. Okay, so we have characterized the better characterization of this auxiliary space, and here this is the full mathematical characterization of the auxiliary space. There's not much point in um, making precise all of these notions here, but maybe you've seen some of these names throughout the summer. Um, but the thing is that after we have all these monodromies, we will say that AD and AU will be related to um, a new object, which is this Seiberg-Witten curve, which is a torus we associate at each point in the moduli space of vacua. And basically, AD and AU will be functions that we take on this torus. And why is that? Why we want to talk about a torus? Because we have this SL2Z duality that we saw before. It is the natural group that transforms a natural group of symmetries of the torus. And also we have the torus, it is described by this tau parameter, and this tau parameter can be related to the gauge coupling, the effective gauge coupling in the theory that we have. So basically, the idea is that we take at each point in the moduli space, we associate a curve. This curve is a torus, and this torus is called the Seiberg-Witten curve. And by operating or taking integrals in this torus, we will actually have the true description of what AD and A are, because we want AD and A to have a nice action under SL2Z, and we want it to have the correct monodromies that I discussed before. So the final step is just finding what exactly is the operation we have to do on this torus to find A and AD. The operation is taking the integral of these differential forms along the loops of the torus. So the torus is something like this, right? And AD will be related to one of the cycles here, and the other A will be related to integrating stuff along the other cycle of the torus. And now we just have to find which function we have to integrate over these cycles to have the A's and AD's with the right monodromies. If we find this function, then the tau parameter of the torus is precisely the gauge coupling of the theory. This just follows from the mathematical definition of the torus in these forms. So it turns out that the answer, the form we must integrate, is given by this ugly expression here. So this is the expression we have to integrate. And integrating this guy along one of the cycles of the torus gives you AU, and another cycle gives you the dual. So basically, this gives the solution. So this is the thing that characterizes A and AD throughout the moduli space of the vacuum. We can check explicitly that A and AD given by these expressions satisfy all the relations that we had previously derived from field theory. And now that we have a formula for them, and we know that the dual A is expressed in terms of the derivative of the prepotential, we just integrate this guy and we find the prepotential. So, okay, so this is Seiberg-Witten theory, and I know that this last few steps is kind of abstract, but the thing is that since we have so much control of the supersymmetric theory, and we can learn a lot about it from field theory perspective, because we know how what are the allowed states, what is the allowed behavior, what is the perturbative behavior, and so on. We can add all of this mathematical structure, which allows us to have a closed expression for everything that we want to say. A closed expression for all the quantities that we want to compute. Um, okay, so just the final some comments about that. Um, the story can be generalized to other gauge groups, as I said. So instead of a torus, and instead of only having two coordinates, A and AD for the moduli space of Aqua, the moduli space of Aqua will be more complex. It will have more coordinates. The Seiberg-Witten curve, if you that we constructed to find the solution, will be a more complicated uh, curve. It will be a surface with more holes in it, more with a higher genus, and so on. But the story goes. You can also do this for theories with matter, to study confinement and so on. And even though everything that I said here looks artificial, looks weird, looks too complicated, or looks too crazy to be true, because let's start it, like we have a few theories, we start like assigning tori to the different points in the moduli space of Aqua. All of these constructions, if you go to string theory, they have a physical interpretation. So if you go to string theory and you want to describe a four-dimensional theory, you have to like compactify some of the dimensions, because string theory lives in 10 or 11 dimensions. You have to compactify stuff, and you have all these branes, because the theories are defined in the branes. Um, and at the end of the day, all of these things are physical objects. In string theory, the branes are physical objects. You have the extra dimensions. They are not auxiliary spaces. They are extra dimensions. And at the end of the day, after you compactify the theory, you will get some curve wrapping around the four-dimensional spacetime, which is the thing we like live in. And this wrapping of the brane is precisely the Seiberg-Witten curve that I discussed about before. So if you're willing to believe string theory, or if you're willing to um, if you think that string theory is cool, then string theory gives you a nice physical origin for all these mathematical um, artificial things or esoteric things that I discussed about today. Um, and of course, I talked here about this super elegant thing of um, using this mathematical structure to compute the prepotential, but actually we can do like a proper physicist's um, computation and just count the instantons directly, or the instantons corrections that I talked about in the beginning directly. Um, of course, this is not easy. It also involves a lot of other math, and but it has been done um, by this guy called this is a professor from Stony Brook called Nikita Nekrasov, and this is tied to the second thing that I want to discuss, which is these topological quantum field theories. I think that I'm running out of time, so can you guys remind me how much time do I have? If not, I can just skip to the end. Okay, so I'll just make some comments, and that's it. Okay, so the thing about topological quantum field theories is just we just start with the the um the thing we talked about in the beginning, the n equals to super nils.
Hello, Joe. Can you hear me?
Yeah, it is. Yeah, I do.
Sorry, I don't know if it's your internet or mine, but I cannot see your screen right now.
Oh,
I don't know if anyone also can confirm this. Okay, so it's my device. Okay, thank you. Well, he was also talking about if he is running out of time or if he has some space of time to finish what he want to
yeah,
present.
yeah. I think I have 5 minutes. They told me. I think.
Okay, sorry. So
Okay,
it's my device. Sorry. Okay, you can
okay, no
continue. Sorry.
problem, no problem. Um, okay, so just very brief words. these twisted, it's usually hard to like define quantum field theories in curved spacetimes or curved space, and because in particular, you want to, one of the motivations for this is that you want to like be able to have a supersymmetric theory in any manifold. This usually has some imposes some conditions on what manifold or what type of space-time geometry you can have. But if you start with d equals 4 n equals 2 spring wheels that we had in the beginning, and you do this thing called the topological twist, which is basically tells you that you reshuffle the or relabel the span of the indices, you can have a theory which has at least one supersymmetry being preserved uh, in any manifold. So the thing is that after you do this, this extra supersymmetry will be a scalar, and it will square to 0. So you have a notion of cohomology from which you can define physical states. And the cute thing about this modified theory is that, so this modified theory, you have you have the field content that we had before, but you reshuffle them, recombine them, they become, they are reorganized in different fields. And the thing is that this action, it can be written as a Q exact term. So it is this Q supersymmetry, scalar supersymmetry, times an expression gives you the action. The fact that you can write the action this way and that um, the theory is invariant under this supersymmetry, it just gives you a lot of power. So the first one is that you can compute topological invariance because you can check that um, the correlators for operators which are annihilated by this supersymmetry, they don't depend on the metric of your spacetime, so you are actually getting topological information about it. And the second thing that is nice is that you can always deform the theory by stuff which is Q of something, and you can make the path integral localize into different regimes or into different sectors of the theory. And in particular, for these topological operators, you can make the theory localize at a certain uh, configuration, at certain configurations, which are these instanton configurations. So this is the starting point for like computing the instanton corrections that I mentioned before directly. So you localize over the space of the instantons, but this is a whole other story, and yeah, that's the rest of kind of of the dissertation in my master's, which is a review of this work. Okay, so I hope that I convinced you guys that Super-Ingles theories, d equals 4 to n equals 2 Super-Ingles theories are rich. So I tried to show you that the low energy behavior of this theory can be determined in an elegant, although kind of complicated way through Seiberg-Witten theory. And this was done by looking at the moduli space of vacua, looking at places, so looking at the states of the theory, seeing how they become massless, and investigating the monodromies of the moduli space, building auxiliary mathematical structures, and getting the answer from them. And at the end, I just made this very quick comment about topological quantum field theories, which compute topological invariance and localize over a particular subset of the moduli space, of the moduli space of fields. Um, so this is not the only interesting supersymmetric leaf theory, so there are many more, as I said. And maybe the most famous one is d equals 4 n equals 4 Spring-Mills, which is dual to string theory ADS 5 times S5. And it was basically the birth of ADS CFT correspondence, which is like um, the the greatest advance in theoretical physics in the last like 30 years. So um, yeah, if I haven't convinced you guys that this is a cool subject, well, at least you have ADS-CFT, and you cannot like ADS-CFT is definitely cool. So, um, okay, so muchas gracias a todos, y well, I hope you enjoyed, and that's it for me. Mm-hmm. Hey, Dennis.
Well, first of all, thank you, Joe, for accepting the invitation. It's a pleasure to
Uh,
have you here
well, thanks for
doing
inviting
this
me.
talk on our little group of theoretical physics that I
Yeah.
hope in the future will be bigger. Well, first of all, well, there's a lot of topics that we still have to cover since we only have seen the first part of supersymmetry stuff,
Mm-hmm.
such as superparticle stuff and what is this model? With Sumino model and that stuff.
Mm-hmm.
However, I think that this is a very good topic to talk about since it's a good idea to introduce these new topics because maybe people will get more interested in this subject since it's very rich, as you said, in mathematical formulation and that stuff. Well,
Yeah.
I don't know if you can maybe also for the people that are listening right now, give some applications, let's say in particle physics or any other possible application that you may know about this system that you have described.
Yeah, as I said, so I haven't discussed this because I'm not an expert. So the thing is that I'm a string theorist, so my kind of motivations are usually different from people in particle physics. So, but one of the things that I said in the beginning is that supposedly you can study confinement in like this theory that I talked about using the Seiberg-Witten construction. I don't know a lot about this, but this is already like a huge um a huge, let's say, um a huge uh yeah, I don't know the word anymore. Not even in Portuguese. So it's a major thing that they accomplished, that they can study confinement in a quantitative way using this setup. Because usually confinement is like happens at the regime where stuff is strongly coupled, and you have it's really difficult to study the theory in this regime, and they managed to do this. Um, so this is like, and maybe this is like a particle physicists, uh, let's say, um, particle physicists good motivation for looking at these model. Um, and also like for supersymmetry in general, this is also something that I'm sure that, well, um, people at people at CERN have been looking for for Suzy, right? They haven't found it, but um, yeah, I'm not sure for particle physics as a whole. It is supposed to like cure some problems, although I'm not sure what problems there are because I'm a string theorist. So yeah, but I think at least confinement and being able to study the non-perturbative physics of just a quantum field theory is already um, good motivation enough to like study or at least try to see what these types of theories have to teach us. Yeah. Yeah, maybe also
Well,
like yeah, because you can have like supersymmetric versions of quantum quantum of QCD, right? Which is supposed to be like the theory for strong interactions. You can have like supersymmetric versions of that. Maybe that and it will be like similar to um, what I talked about here because it was also Yang-Mills theory. You have to add matter and stuff. So that's another yeah.
well, again, thank you, Joao, for your great talk. I hope to see you in the near future, maybe giving a new talk on string theory, since this is your topic that you are most
Yeah,
interested
yeah.
about, right? So,
Yeah, it
well,
will be cool.
again, thank you. Obrigado pela apresentação. Até mais.
Obrigado, man. Até mais.
Well, I have a question about the topological invariants that you mentioned.
Yep.
I would like to know which are the most important topological invariants in these topological quantum field theories, and what they can tell us about the theory or about the physics involved in those theories.
Okay, so here I think that so I'm also not an expert about the maths in this, but the thing I know is that this is supposed to be connected with something which is called Donaldson-Witten theory, and in particular it computes these things called Donaldson invariants of a manifold. I don't know what these are good for. These are like things that mathematicians are interested about. Um, and but they are supposed to like be they're supposed to be numbers or quantities that characterize these curved manifolds in some way, in some sense. Um, from the physicist's point of view, topological theories they are usually like cool because they are simpler. Um, well, in some sense they are simpler. You have like more control about um, the configurations you're dealing with, or you have more control about how to make computations and stuff like that. Um, and here in particular, I think that the fact that this is well, at least from this particular perspective for this particular case, the important thing is that um, because this is a topological, well, localization is this localization phenomenon is something that is I'm not sure if it's like I don't think that it is um, just for topological field theories, but it happens here. And for me, the main point for physics in this model that I showed is that because you have localization, this is what allows you to compute these instanton contributions in a reasonable way. So usually when you have a quantum field theory, it's usually complicated. You have to like you only have access to the perturbative regime. Getting non-perturbative knowledge about the theory is difficult, as I said in the context of Seiberg-Witten theory. But here, because you have this localization um, of the theory into this um, sector of the field configurations, it allows you to compute by hand or like to actually compute these things which would be inaccessible through like usual methods. And yeah, so basically this is like a consequence of the action being Q exact in this sense. So yeah, And the action being Q exact implies that this theory is topological. So yeah,
Okay, thank you very much.
yeah, thank you.
So if there is no more questions, we can finish here. Thanks a lot
Yeah, sure.
again, Joao. It was a
Well,
pleasure to have you here and to accept the talk. Um, for the people here, in some minutes, we are gonna have another talk. So stay here, please. Thanks, Joao.
okay, thank you guys so much for inviting me. And if anybody wants to like talk later, I think the organization has my email, so just feel free. So thanks again, very much. Bye bye.
Hola.